So again, my name is William Dawn. I'm from NC State. I am a PhD candidate in the nuclear engineering department, and my advisor is Dr. Scott Palmtag. I'll be talking about unstructured finite element neutron transport using MFEM. I'm going to begin by thanking everyone for coming. I think all the time zones have had lunch at this point, so I appreciate everybody coming back, and hopefully this won't be too terribly boring. So this is what I'm going to talk about today. We've seen a lot of mathematics, and this is more of an engineering application of it. So I'm going to show you how we're using some of these tools that the MFEM team has developed. So I'm going to start with an overview. So specifically for our work, we're interested in modeling microreactors. It's a new class of reactor for electricity that the DOE and DOD are interested in. They're very small, with an electric output of approximately 10 megawatts, which is about 100 times less than typical power reactors. They're physically small, so we need to resolve geometry within them. And there's a variety of designs, so we need a versatile solver. Some of them use different neutron fluxes, different energies, spectra. There's a variety of cooling designs, fluid flow, non-fluid flow with heat pipes, and then there's some of them being investigated for space applications. So we might not even have gravity in some of our models. So we're looking for a versatile solver. So as an example, and I'll show some results from modeling this reactor, is the Marvel microreactor. It's being developed at INL, and they're going to build it on site. So this one's very small electric output with 18 to 25 kilowatts electric. It's also physically very small, about a ½ meter high and about 1 meter in diameter. It's fueled with uranium zirconium hydride, high assay, low enriched uranium, HALEU. Because of the hydride, and there's a lot of beryllium in this reactor as well, the reactor operates with a thermal neutron spectrum. So there's a lot of neutron scattering. And when we have a lot of scattering, we need good resolved geometry as well. This particular reactor is cooled with liquid NaC. It's a metallic eutectic coolant. I'm not going to talk about that. Fluid flow is a different problem, but just for your information. So why are we using MFEM? Well, we're working with the Exascale Computing Project, so that's important. And we needed GPUs to work. So we needed a finite element framework that had GPU support, and we picked up MFEM. And it's been a great experience so far. So first of all, we needed library support. So Zanio hit on this morning, where we were linking to all of these libraries and more to run some of our problems. But the biggest thing that stands out from MFEM from a user's perspective has been the rapid prototyping. I'm going to show you some results, but to get here, we've investigated probably 24 different solver methodologies and different algorithms to get there. So being able to start the day with an idea and finish the day with a new implementation that can run on Summit is huge. So just being able to test all of that has really been a game changer in using MFEM for this project. So now I'm going to move on to actually talking about what we're modeling. So this equation here is the continuous form of the neutron transport equation. It's a steady state Boltzmann transport equation. It's supported by a 6-dimensional phase space, 3 dimensions in space, 2 in direction or angle, and 1 in energy. You can think of it as 3 in space and 3 in velocity, but for reasons we have to split them up basically. This is an eigenvalue problem for an eigenvalue lambda and an eigenfunction psi. These coefficients here, capital sigma, are what I call cross sections. They're basically interaction probabilities. So they have units of inverse centimeter, 1 over centimeters. So the first thing I'm going to do is discretize the equation. This is not novel, but this is just so we're all on the same page about what I'm solving. First thing we do is split it into a finite number of energy groups. Typically for our work, it's about 24 is good, maybe up to 200. So we have now group-wise fluxes and group-wise cross-sections, so group-wise material data. And we're replacing, so I'll discretize angle next, and you'll see all of the integrals are getting replaced with summations. So in angle, we discretize using a discrete ordinance approximation. I think I've heard a couple other presenters talk about this today. So we pick a quadrature set, we pick a discrete number of angles and solve along those angles. This graphic here is an example of one of the quadrature sets that we can use. This is what's called the level symmetric quadrature set. It's order 10, so it's the S10 quadrature. And this is the angles plotted in the first octant. This is what the transport equation ends up looking like after we discretize in energy and angle. You'll notice all of our integrals are gone. We have these summations now, and everything is just a function of position at this point. So that's great. So now we can toss it into an FEM framework. I will point out that when using these angular quadrature sets, the number of angles in the quadrature grows quadratically with the quadrature order. So it can become overwhelming very quickly, the number of angles that are required to solve a problem. So S10 is actually probably decent, but some of the results will go out to S16 typically. So the number of angles that we're solving can become very large very quickly. And I'll point out right here, we'll get to it later, but this leading term is a problem with using the finite element method. So we've discretized everything out, and now we have a discrete phase space. So this is kind of what's unique about the neutron transport equation. We've seen some other fluid flow stuff where you would have 3 dimensions in space and 3 in velocity. Well, we have this high dimensional continuous phase space, and that falls down into a high dimensional discrete phase space. So for example, and this is what I call the vector dimension. This is some of the MFEM terminology coming through. So for example, if we have 24 energy groups and use an S10 quadrature set in 2 dimensions, so like a 2-dimensional simulation, we multiply this out and we end up with 1,440 unknowns per grid point. So these numbers get pretty crazy pretty fast. I'll show you results that have more unknowns than this. So this is not a contrived number. This is a realistic number, and we can very quickly have thousands, probably tens of thousands of unknowns per grid point. What this shows is that most of our DOF are going to come from our energy and angle discretization, not from our spatial mesh. And because of that, our work is currently restricted to investigating linear finite elements, because we're going to have a hard enough time solving, for all of our vector dimensions at each grid point without the introduction of higher order finite elements. Because we're sticking with linear right now, spectral methods are probably not going to be helpful. So we're still doing this is some very classical FEM. We're just trying to get Exascale to help us, basically. So I pointed out earlier that leading term is going to be an issue, and that's because transport equations, as we all know, are hyperbolic. And so we have to do something if we're going to solve them with a finite element method. What we do here is called the Self-Adjoint Angular Flux, or SAAF method. This converts the hyperbolic problem to an elliptic problem, and we end up with a second order system of PDEs that we can solve with continuous finite elements. So now the leading term has this grad term instead of just a single grad. This is exact. I haven't done the derivation here, but this is exact, and it's a valid approximation, or it's a valid formulation. And notably, so we can use continuous finite elements, and we don't need a sweep when we use the SAAF method. We can just dump this into our FEM framework, MFEM in this case, and run with it. So again, this is still an eigenvalue problem for eigenvalue lambda and eigenfunction psi. So I think we all know that it's not enough to just show equations and then say solve it when we're talking about exascale computing. So you have to talk about how you're going to go about solving it. We've investigated 2 main classes of solvers. First is the generalized eigensolver. This is what we would categorize as an all-at-once method, where we build everything, put it in these enormous matrices, pass to SLEPC, and wait for an eigenvalue to come back. In our work, we like the generalized Davidson algorithm. Works pretty well. There's other work that shows why it's good for transport problems. We're using GMRes as a preconditioner, and right now it's hooked up to the AMGX library to run on GPUs. We're working on hooking it up to for GPUs, but right now we've been getting good results for AMGX. Problem is these matrices are enormous. The number of angles is quadratic with the quadrature order. The number of non-zeros is quadratic with the number of angles. So the number of non-zeros is quartic, ON4, with the quadrature order. So just your angular quadrature can drive you to literally need more memory than is available on the GPUs. So that becomes a problem. The alternative is source iterations. We solve one energy group at a time and then converge that energy group, move to the next one. It ends up with a Gauss-Seidel convergence in energy. So it's not as fast, but it's pretty good. And the problem is, though, we have to use a lagged source term. And so what that means is we have to introduce scattering iterations to converge the source before we move to the next energy group. This is SPD, so we're using hyper PCG and hyper boomer AMG. So that's fun. But the problem is you end up calling your PCG solver about 10,000 times. So that's going to always be a runtime issue. The other issue here is these matrices can get so small, actually, that it can be hard to have meaningful work on each processor. And so we end up having trouble with scaling and parallelism as well. So this is how we get to that 10,000 calls to our PCG solver. The trick is that the solve is at the most nested level. So we have to do 15 scattering iterations for about 20 energy groups and about 40 power iterations. So you multiply these numbers together and it's pretty easy to get to 10,000 iterations. We spend all of our time doing steps 6, 7, and 8 here. 8 is a solve, so that's pretty easy to speed up. Let's pass it to Hyper on the GPUs. 7 is actually assembling the linear form. And we've been getting a lot of great support from the MFEM team. I'll give a shout out to John Camier, who has been instrumental in getting this. We're doing some tensor assembly stuff on the GPUs. Number 6 is not clear how we're going to do that because it needs some material data and stuff. So that might not get offloaded to the GPUs. So I talk about these two methods that we've investigated. And I just want to point out they're basically limits on the spectrum of how much. So if you want to be more efficient at the cost of using more memory, the limit is generalized eigensolver. If you want to do more matrix-free math and use less memory, the limit is source iterations. There is a space in the middle. It's not clear if that's beneficial at all. There would need to be research done here. So we're looking at these two limits right now, basically. Someone else could try to pick this up and run with it, but that's not our project right now. So now I'm going to actually show you some results. I said I'd show you some Marvel results. So we generated a series of meshes with Gmesh. We have 24 and 238 group cross sections. All of the results here with 24 groups. If you're paying really close attention, there's an inverse interaction probability, a 1 over your cross section. That's a problem with your conditioning, your system conditioning in gaseous regions where you don't have a lot of interactions. So we've just artificially increased the density, the interaction probability in that region, just to get some results out. So I'll show you results for this R2 mesh here that has 3 million vertices. R3, we are not able to load into memory yet. We're working on it. We're going to need to get Pumi hooked up to be able to run with that mesh. It's very big, and we have to split ahead of time. Tiziano pointed out this morning that that's something they're actively working on in MFEM. So we're excited. This is what the reactor looks like. There's a fuel region in the center. And then there's this region where we have these drums that can rotate to bring neutron absorbing material closer or farther from the core. So this is what it looks like. These are the eigenvalue results. So the first thing we try to do is figure out if our eigenvalue is converged in space and angle. It's harder than it seems. So for these results, we had to use the source iteration solver to fit everything into memory. And the most refined results here are this R2 mesh with the S6 quadrature, and that needed 256 summit nodes, which was 10,000 MPI, and that ran in about 6 hours. We would like to get more spatially refined results. We're going to work on getting that R3 mesh running, but I don't have them for you today. And in space, we're observing a convergence rate of about 1.34. So these most refined results we have are 1.82 billion. Remember, that's from a 3 million vertex mesh. So a lot of DOF are coming from our energy and angle. And I have an asterisk here. We've got some preliminary results for this refinement. And if we get that to run and get those results finalized, those will be the biggest SAAF results ever run. This is what the neutron distribution looks like. So neutrons are born at high energy in the fuel. They spread out a little bit and slow down and thermalize. And then they thermalize farther. There's a lot of scattering material here, and they basically die here and they don't go much farther. I'll mention this briefly. So we're using linear finite elements and we're describing curvilinear geometries. So that's a problem. So when we refine our mesh, we get, the FEM benefit of having more nodes and decreasing characteristic mesh size, but we also get a better description of our geometry. So it turns out that when we use really coarse meshes and don't conserve the mass in the reactor, these really coarse meshes can have big fuel errors. That's a big problem. So we're looking at, maybe we can do treatments to try to conserve the mass, which is great. And it does improve our results by about a factor of 2. But we lose some of those FEM convergence properties and we don't get monotonic convergence anymore. So it might be good, but we're going to start to lose our convergence properties. But these results do show that we really do need to be conserving mass in the reactor. Eventually, we want to run a 3-dimensional model. This is basically an extruded model with some steel on the top and the bottom. We're not there yet. It's hard enough to run 2D. And so we think we will get 3D results. We think we're just going to have to use probably coarse mesh and coarse angle approximations. But we do want to demonstrate, MFEM is this great tool, and we want to show that once you get your 2D model working, you're, a couple hours away from running it in 3D. So what are we working on right now? I think everybody's working on using GPUs better. And so we're passing as much as we can to Hyper and getting our GPU settings tuned properly. And then this is, again, John's helping a lot with this. Some partial or tensor assemblies of the linear forms on the GPUs. We're seeing some pretty incredible speed up here once we can get that working. Getting large meshes to work by linking with Pumi. We're going to add heat conduction. That it almost sounds like an afterthought, and it kind of is, because MFEM is so great that we just have to solve an extra Laplace equation and then couple our feedback in. And then we're going to get some demonstrational 3D results to show that, hey, we can run 3D problems. We just need a bigger computer, probably. This has been funded by ECP, and we used Summit through the OLCF at Oak Ridge. Again, I want to thank you, everybody, for coming back from lunch and listening to some neutron transport.